Welcome to the Explainer. Let's just dive right into this. For centuries, cartography, the incredibly meticulous art and science of mapmaking, has been this strictly human-driven endeavor. It's been governed by rigid rules and expert design. But today, we're looking at a completely new futuristic era. We are going to explore how artificial intelligence is quite literally rewiring this ancient craft, moving us away from the drafting table and straight into the realm of neural networks. So we gotta address the elephant in the room right off the bat. Just as we've seen generative AI creating text and images in seconds, we have to ask, is a map GPT going to replace cartographers entirely? Like, is an AI going to take over the entire workflow from the initial conception of a map all the way to its production and distribution? Well, that is exactly the question our source material, Chapter 20 of Jochen Shiva's textbook on cartography, really seeks to figure out. To unpack all of this, here is our roadmap for today. First, welcome to Ch20 AI. Second, rules versus data. Third, the machine learning pipeline. Fourth, AI mapmakers in action. And finally, the black box problem. Section 1. Welcome to Ch20 AI. We're entering this highly multidisciplinary era, but what exactly are we talking about here? Ch20 AI is defined as the application of artificial intelligence to geographical data to accomplish spatial tasks that would usually require human intelligence. And why is it stepping in right now? Well, conventional cartographic methods are hitting some severe bottlenecks. They often only provide partial solutions to incredibly complex problems. So Ch20 AI steps in because it absolutely excels at automating repetitive tasks and spotting invisible spatial patterns across massive datasets, what we call big data, usually sourced from remote sensing and open geoportals. Moving into Section 2, rules versus data. This is where we really see a massive paradigm shift. There's a fundamental philosophical difference in how a machine actually constructs a map compared to a human. Traditionally, in the conventional approach, a human creates a specific rule, applies that rule to the data, and gets an output. But with machine learning and deep learning, we don't give the machine a fixed method at all. Instead, we feed it training data, meaning both the input data and the expected results, and the machine actually generates a brand new model. It figures out the method entirely by itself. So the big takeaway here is the contrast between top-down and bottom-up. We're moving away from these centuries-old, top-down, rule-based, expert systems where cartographers dictate every single drawing threshold. Instead, we are adopting a modern, bottom-up, data-driven approach. The machine is studying thousands of examples and figuring out the solutions and regularities completely independently. It's a total game changer. Now, you probably hear machine learning and deep learning thrown around a lot. What's the actual difference? Machine learning still requires a little bit of human handholding. Humans actually have to extract features from the data before the machine can learn from it. Deep learning, on the other hand, goes much further. It uses deep artificial neural networks, like convolutional neural networks, to handle massive amounts of completely unstructured, raw data, like pure image pixels. It extracts those features on its own, though, their warning, it requires immense computing power to pull that off. Section 3, the machine learning pipeline. Let's see how this actually works in practice, almost like an AI factory tour. The pipeline consists of 4 main steps. Step 1 is data preparation and enrichment. So for example, if we're mapping the spread of COVID-19, we wouldn't just use raw health stats. The AI enriches that data with things like population density and travel patterns. Step 2 is feature extraction, where the system isolates the relevant signals. Step 3 is training and generating the actual ML or DL model by tweaking its internal parameters. And finally, Step 4 is the output, or inference, where the finished model makes predictions on brand new data. But there is a massive hurdle right in Step 1. Encoding. An AI cannot inherently read cartographic vector data, the beautiful sharp lines and shapes that humans draw. It has to translate them into machine-readable formats. A really common method is simple raster encoding, which essentially turns the map into a grid of pixels. But that rasterization can unfortunately cause a significant loss of spatial information. It can break road networks or round off buildings. Because of that, researchers are actively exploring more complex raster layer and graph encoding to try and preserve that underlying geometry. So the model is training, but how does it actually know it's doing a good job? Enter the loss function. This is a highly technical concept, but essentially, it's a mathematical tool that grades the AI on its homework. As humans, we have to weight this function to tell the AI exactly what to prioritize. Back to our COVID-19 map example, we have to mathematically balance competing priorities. Do we want the AI to prioritize the exact spatial localization of a single case or the broader regional accuracy of the overall outbreak? the AI meticulously adjusts itself over and over to minimize this loss. Section 4. AI mapmakers in action. So, what are these futuristic systems actually doing in the real world today? There are 4 main cartographic tasks AI is currently tackling: object and pattern detection from satellite images, automated generalization of map features, map style transfer, and the notoriously difficult task of label placement. The machine treats each of these not as some subjective art project, but as a highly complex optimization puzzle it's learning to solve. Let's look a bit closer at automated generalization. Normally, a human codes strict thresholds to simplify a map when zooming out, but AI learns generalization just by looking at examples. By studying thousands of before and after map scales, it naturally learns that, say, several small, adjacent buildings should be combined into one large block. It is genuinely amazing to watch it mimic human cartographic behavior without ever being taught the formal rule. It's definitely not flawless, though. Rendering presents some very real-world challenges. Remember that rasterization issue we discussed earlier? Because the AI processes data as a pixel grid, it can lose vital geometric info. When you compare the sharp, perfectly straight ground truth edges of a building to the slightly warped, blobby predictions made by a deep learning model, you see the problem. Keeping right angles perfectly square is still a major hurdle for AI. Another really fascinating application is style transfer. AI neural networks can actually be trained to look at the specific visual aesthetics of something like Google Maps and instantly transfer those exact colors, symbols, and styles directly onto raw open source data like OpenStreetMap. It is an incredible time saver. However, we do have to contrast that kind of magic with areas where AI still struggles, like the highly complex, nuanced task of assigning the perfectly appropriate label size for text on a map so it doesn't overlap everything else. Which brings us to Section 5, the black box problem. Our source text highlights a really fundamental critique in this evaluation phase, stating the outputs generated are data-based, and the decisions made are generally not comprehensible. This really gets to the heart of the black box nature of artificial intelligence. Unlike traditional methods where we wrote the rule ourselves and know exactly why a row was drawn a certain way, with a deep neural network, we often have absolutely no idea what logic the machine used to render a specific map. And honestly, that lack of transparency is a serious problem. Enter XAI, or explainable AI. This is essentially the necessary solution to the black box issue. XAI involves building transparent models and interfaces designed to actually show humans how the AI makes its decisions. The European Union's AI Act is actually pushing hard for this kind of transparency right now. In the cartography world, this could soon lead to explanatory maps that visually justify the AI's cartographic choices back to the user. Because at the end of the day, the AI doesn't actually know what makes a map good. AI currently lacks formalized, explicit cartographic rules, which means human experts are still desperately needed. Humans have to select the proper training data, inject actual cartographic knowledge into the models, and rigorously evaluate the machine's output to make sure it isn't just generating geographical nonsense. We are absolutely not at an end-to-end, fully automated MapGPT solution just yet. Which leaves us with a pretty powerful, provocative thought to end on today. As we watch these data-driven models evolve at lightning speed, we really have to ask, is the ultimate mapmaker of the future purely a machine? Will it remain a human, or are we looking at an inseparable hybrid of both? It fundamentally reshapes how we view the world. Keep that question in mind the next time you open up a map on your phone. Thanks for joining me on this explainer, and as always, keep learning.